for Nash Equilibrium.
Thank you. Hello everyone. This talk is on complexity results for multiplayer Nash Equilibrium. So let's start with the games. In a game, we know we have a set of players, and each player has a set of moves, which we call strategies. So in rock paper scissors game, we have 3 strategies, and when everyone plays their strategy, then they get some payoff. And it may happen that there is no single strategy which is best for a player. Like in rock paper scissors game, there is no single strategy which is best for any player. So they are allowed to randomize among their strategies. And under randomization, Nash in 1950 proved a very beautiful theorem that there always exists a stable state where no player gains by unidirectional deviation. And this state we call Nash Equilibrium. And if the game is symmetric, meaning that if the identity of player does not matter, like in a rock paper scissors game, like set of strategies are same, the payoff is same, then there exists a strategy, there exists a stable state where everyone plays the same strategy. And this is called symmetric Nash Equilibrium. And these results were obtained through via fixed point theorem. Like there is a function from a compact set to a compact set, and there is a point. Whatever continuous function you take, there is a point which is fixed by this function. So this is the fixed point of this function, and this is non-constructive. We don't get any algorithm out of it, meaning that how to get such a point. So, and there has been a huge amount of work in economics as well as in computer science to derive algorithms and complexity results for these problems. And towards this, Papadimitrov in 1994 defined a complexity class called PPAD, which captures the problem of computing approximate fixed point problems. Like here, like you want a point x such that fx minus x is like within epsilon, like you allow epsilon at for the fixed point. And here the solutions are rational. But note that as Tusha also mentioned that we are interested in the exact fixed point. Suppose you are interested in the exact fixed point, but this approximate fixed point can be very, very far away from the actual fixed point, even if like epsilon is exponentially small. And for the exact fixed point, Elisabeth Yanagakis in 2007 defined another complexity class called fixed P, which captures the fixed point computation problem of algebraic functions. And here the solutions, all solutions can be irrational but algebraic. And let's see where they sit they are related to the traditional complexity class. So this is like function class of NP, but I am just for simplicity writing NP. So PPAD sits inside NP, but fixed P is not known to be in NP. But everything is sit inside P space, and fixed P is believed to be harder side of P space. Okay, so this is this is what we know about the Nash Equilibrium computation. That for the 2-player games, we know that the solutions are rational. Finding one is PPAD complete in a series of remarkable papers. And for more than 2 players, like 3 or more players, all Nash Equilibrium would be irrational but algebraic, and finding them is fixed complete. So this was about like computing in Nash Equilibrium, where we know that there always exists a Nash Equilibrium from the Nash theorem.
Good question. When you say it's on the harder side, the P space, wouldn't that mean it contains a P space complete problem? That can't be true.
Because fixed P is again a total class. Yeah, so.
That's what you mean it's on the harder side. I mean,
I think it's fair to say we don't know. We
don't know, yeah.
So it's not known to be. It's not known to be in the polynomial time hierarchy. It's not known to be in anything. So from a classical complexity class point of view, anything significantly better than P space.
So this is just with personal communication with the analyst. You said that like it would be that.
Okay.
Yeah.
Okay. Okay.
Okay, so this is fine. Okay, so this was about like computing in Nash Equilibrium, where we know there exists a Nash Equilibrium. So what about the decision problem? There is no decision to ask whether there exists a Nash Equilibrium or not. So for the decision problems, we can ask whether there exists a Nash Equilibrium where every player gets payoff at least h. H is some given number to you. So let's denote this problem, max payoff problem, and we can also ask whether there exists a Nash Equilibrium where player I plays a strategy like with non-zero probability, and those strategies are a superset of some given subset Ti. So let's call it superset problem, and similarly we can define subset problem. So these are the decision problems. whether there exists a Nash equilibrium which satisfies this property or not. And another thing is that whether there is more than one Nash equilibrium. So it's like whether the Nash equilibrium is unique or not. So this is another decision problem. And finally, we also consider this decision problem whether you ask whether there exists a Nash equilibrium where every strategy is played with at most half probability. So let's denote it by inbox. And before I go to the complexity of decision problem, let me define one more complexity class called ETR, which stands for Existential Theory of Reals. So here, like this is a multivariate polynomial in 3 variables, right? Suppose you have n variables and m multivariate polynomials on n variables, and the question is whether there exists an x, candidate x, in reals such that it satisfies all the multivariate polynomials. So it's like simultaneous zeros of all these multivariate polynomials, and this question is in ETR. Okay. So, and where is ETR sits here? So ETR contains everything here, but it is inside this space. And this was also very surprising when it was proved, like in 67.
No, contained in P space is actually the 80s.
Yeah, it is ME, right? First, like it was like proved to be decidable in 60s, and then it was proved to be in this. Okay.
Decidability is just the task piece.
Yeah, task. Yeah. Thank you. Yeah. So for the decision problems, we know that 1 through 4, these 4 problems, the first 4 problems, they are NP complete for 2-player games. When you ask whether there exists, there are more than one Nash equilibrium and so on, they are NP complete. And 5, the 5th problem for more than 2 players, like 3 players, is known to be ETR. And it is nothing is not about 1 through 4. These 4 standard problems. Huh? I think it has not been studied. It's expected to be. Okay, so this is one question we consider here for the complexity of these 4 decision problems in games with 3 or more players. And the second thing is like let's talk about the symmetric games. What we know about symmetric games? Again, for 2 players, solutions are rational, complexity is ETR-complete, and the decision problems for 1 through 4 is again NP-complete. And for more than 2 players, again algebraic, it is known to be in fixed P, but whether it is fixed P hard, this is one question we consider, and nothing is known about the decision problems. And in fact, this complexity was obtained through by a simple reduction from non-symmetric game to a symmetric game, which I will come in a short while. And Papadimitriou in fact asked whether there exists such a reduction for more than 2 players. So we settle all these questions, and we essentially saw that for games with 3 or more players, our first reduction reduces in box to all these 4 decision problems, and we get ETR hardness for all these 4 problems. And our second reduction reduces the non-symmetric game to a symmetric game, and we get fixed P and ETR hardness for symmetric Nash Equilibrium computation. In a symmetric game of 3 or more players. Okay. So before I go into the reduction, let me first show you how the games are represented. So for 2 players, we have like suppose there are for 2 players there are like Alice has 2 players, Alice and Bob. Alice has M strategies, Bob has N strategies. So we can represent this game by 2 pair of matrices, where Alice is playing a row and Bob is playing a column. And if they are playing this row, this column, then this is the pair of this entry is the pair of Alice, and this is the pair of Bob. And so this 2-player game can be represented by 2 pair of matrices. For K player, we will need K-dimensional tensors for each player. So this is how the game is represented for multiplayer. And as I told you before that, the players are allowed to randomize among their strategies. Suppose X is the probability distribution of Alice and Y is the probability distribution of Y. Then we said that X, Y is a Nash equilibrium if there is no unilateral division. So I'm not defining mathematically, but I hope you understand this. Okay, so let's come to the reduction one. So I'll show you only this reduction involves to max payoff, and that too for the 2 players. So I'll only give you the main ideas, and yeah, so that will be enough to you to I think complete the course. Okay, so we want to show that if there exists a Nash equilibrium where every strategy is at most one half, if and only there is a Nash Equilibrium with every player gets at least H payoff. So suppose we start with this game, we can assume without loss of generality that the payoffs are non-negative. So we reduce this game, we construct this game, this big game out of this game. We embed NP such that this is one entry A plus H. So we add S to every entry of A. And now we create n more blocks of A. So in the first block we are adding 2H to the first column and so on. So there are n plus 1 blocks of A here, where okay, so and here it is -1 and it is 0. And similarly we construct the payoff matrix for the second player accordingly. Now we show that if there exists a Nash Equilibrium here with every strategy at most half, then there is a Nash Equilibrium here with payoff at least H. And this is it and only. So one thing is clear that what happens that if you take any Nash Equilibrium here with at least half pair, where every strategy is at least half, and you just restrict you construct a Nash Equilibrium here by just taking the same distribution, same probability, and these probability will be 0. So this will be the same thing, and you can see that if this is the Nash Equilibrium of this game, then of course both of them are getting at least Nash Equilibrium. So this is easy to see. But let me show you the other thing. If there is no Nash Equilibrium here with where every strategy is at least half, then you will not get payoff H here. Yeah, it must have. Sorry. So what happens here that suppose we try the same thing. That suppose the first strategy is played with 0.6 probability. Then what happens if we try the same trick? Then what happens that this 0.6. So the row player is getting a y plus H. But here it is 0.6. So the row player can move to the second block because he is getting a y anywhere. But here now from the first column it will be 1.2H. So he has incentive to move from the first block to the second block. And similarly, if the row player is moving to the second block, then the column player will move from first block to the block ahead because he is getting -1. So this is not the complete proof, but if you, this is all the ideas. Okay, so that's how we get the ETR hardness for all these resistance problems. And let me talk about the reduction too. So for that, let's first see how we do it for the two players. So for the two players, we take any non-symmetric game. We just create a symmetric game by plugging in and we transpose like this. So in a symmetric game, you can see in a symmetric game there is only one matrix because it is the same matrix for both the players. So this I think you have studied and seen this reduction. And here what happens that if xy is the Nash Equilibrium of this game, then ww is the symmetric Nash Equilibrium of this game, where w is xy. And this is it and only. This is how we do it in two player case. So, yes. So let's do the same trick for the three players. So now we have three tensors A, B, C, and try to plug in the similar way. So what happens is that if xyz is the Nash Equilibrium here, then we can get ww is the Nash Equilibrium here, but the problem is that w is only x00. We cannot make sure that all these vectors these sub-vectors, they are also non-negative. They are also positive. So this is the difficulty in getting such a reduction from non-symmetric to symmetric. So for that, what we do, we construct a GAN gadget. So it's a simple GAN. It's a 3 cross 3 cross 3 GAN. So I am representing tensor as these three matrices. And there are three non-zero entries. So this is a simple symmetric GAN, and you can easily show that the only symmetric Nash Equilibrium of this GAN is 1/1. Okay. Now, if I plug in these A, B, B, C, C, some non-negative numbers at these locations, and it is again a 3 cross 3 cross 3 GAN, then we can show that if alpha beta gamma is a symmetric Nash Equilibrium of this GAN, then all alpha beta gamma are positive. It means that it has full support symmetric Nash Equilibrium. Because this is a simple game, you can like just do some algebra and do it.
So whose payoff is this?
This is because
It's symmetric. It's symmetric. It's a
symmetric. It's a symmetric Nash equilibrium.
And that means alpha is equal to beta is equal to gamma.
No. It can depend on the ABC.
Alpha, beta, gamma are numbers, they are not vectors.
Oh, I see.
Oh, these are
That's
numbers.
So the single symmetry.
Right. These are vectors. Okay, so now what we do, we take any three-player game, non-symmetric. We embed, we have this gadget. So we embed these tensors in these gadgets. So now we have to blow up these entries, 1, 0, and 1 accordingly, such that they become tensors, and B here, C here. And then we show that if XYZ is a Nash equilibrium, then WW is a Nash symmetric Nash equilibrium, where W is XYZ. This is how we do the reduction. And this gives us a fixed P and ETR as well. Symmetric Nash equilibrium multiplications. Okay, so to end my talk, I don't have much time. So two open problems. So one is like we know that there always exists a symmetric Nash equilibrium and symmetric Nash. Non-symmetric Nash equilibrium may also be there or may not be there. So what is the complexity of deciding whether there exists a non-symmetric Nash equilibrium in a symmetric game for 3 or more players? I think for 2 players it is recently been proved to be anti-complete for 2 players.
Have you tried the annotation games? I mean, what's the name of them? Do you know what I'm talking about? I mean,
The imitation game like that, it's secondary identity.
Yeah. Right. So there, if this is a biometrics game, it's equilibrium exactly the.
No, this is about 3 or more players.
Yeah, exactly. So have you tried something like this or something?
Maybe, yeah.
So you try to get like ETRs or NP1? I mean, the NPR follows from the 2-player, right?
Yeah, NPR for probably ATR. I expect it to be ATR. And the second question is like complexity of counting number of Nash equilibria for 3 or more players. For 2 players, it is not to be sharply complete. And that's it. Thank you.
Questions?
In 2003, Jugal Garg proved that every real algebraic variety can be encoded in. There's a you can have 3-player games that are essentially the Nash equilibrium corresponds to any real algebraic variety.
So you are saying that for any algebraic variety, there exists a game,
3-player game that has that real algebraic variety.
And
So, I mean, don't your results follow from that too?
It's not all, Dante's result is not saying that the set of all Nash equilibria can be made into any real algebraic variety. It's saying something subtly different.
I am saying about decision problems. Right? So I am saying
Yeah, but I mean, I think my understanding is universal that any real algebraic variety is actually equal by 3-player games.
It's, if I remember correctly, maybe my memory is wrong, but it's basically the space of mixed strategies of one of the players.
Completely mixed.
Yeah, the space of completely mixed strategies of one of the players, right? So there's some conditions. It's just there are some, but yeah, that's an important result. But it's not sort of if you're thinking that maybe it implies some of these fixed P results.
In particular, ETR is ETR-completeness is essentially what I'm worried about.
Right, but.
yeah, we can talk. I'm not aware of that thing, so we can talk about that. Yeah.
Is there a class in like a sharp ETR? Or like, is there
I don't know.
other class
There
for
is-
algebra?
Sharp ETR.
there is something like that. Yeah. Sharp, R.
So then it should be probably
Yes,
sharp.
something like that.
Yeah. Any more questions?
Yes, thanks. So I